Hey guys, it's really frustrating. I'm recording this video now for the second time. It was like 30 minutes long, and at the end of it, I had no audio. Anyways, just a little announcement. I am going to be making a new website, edwinfairchild.com. I'm going to post more videos. I'm going to remake the videos for my STM32 series. But in the meantime, I'm trying to figure out the WordPress and all that crap. I'm not really interested in web design, but I have to figure it out so that I can make a half decent looking website. In the meantime, here's a quick, maybe not quick, probably like 30-minute video on how to do this, and it's not that hard. You can skip it if you want because I'm gonna go through all the settings, why I'm doing what I'm doing, etc. Complete beginner kind of stuff, okay? But what this video is going to cover is a function right here, print a message, right? As you can see, it's a short function, and it allows you to use regular printf style nomenclature or whatever you want to call it, where you can type things like %d and then comma and then give what you want %d to equal, and then you can print that into your serial port on your computer, and you can use it to debug or whatever it is that you want to do. You are going to need something like this software right here, which is called AccessPort, and you can get this at this website, SUDT or whatever, or you can just Google AccessPort serial.com. It should come up with this website right here. You click on it, you go here, you download it. It's free, it's small, and that's that. Quick rundown. You're gonna go to this little configuration tab. You're gonna tell it what COM port you're gonna use, the baud rate, everything else default. I've never touched anything else because I always use 9600 kilobytes, and that's it. How do you know what COM port you're going to use? You're going to go to your well, here, let me tell you. You also need to buy a USB to serial adapter, right? These things are $5 or $6 on Amazon. You go to eBay, you can get them even cheaper from the motherland, China. All right, and how this works is basically you have this little thing that plugs into your computer, and it has 5 volts here, 3 volts here. You're not going to need to do that because you're going to power your microcontroller via your ST-Link anyways. But you will need this ground connection. The RX of this thing goes to the TX of your microcontroller, or the TX pins that you will assign, and you'll see that in just a second. And then the TX of this adapter goes to the RX of your microcontroller, okay? So remember, the TX goes to RX and the RX goes to TX, and that's how that's going to work. And they're relatively cheap. It's good. It's a good way of debugging. And I'm going to make another video on debugging using actual the Kyle here and looking at your registers at what you're actually setting. If you look here, for example, you can go through here and it's a GPIO. If you go here, GPIO, you can see the settings that you've made. Here's the control high register. Here are the settings that I've made, etc. So that's another way of debugging in this, and you can look at your stack pointer, your registers. You can watch memory locations, etc. That's another good thing to learn, and I'll cover that in a different video. Okay, so yeah, so that's that. All right, so now let's get into the code. Okay, you're going to need these three. You're gonna include these three libraries: strings, standard lib, and standard arguments.h. Now you don't have to install anything because these are standard libraries that come with the C language. So just include them and it'll work. We're gonna make a define debug UART1. You don't have to, but you can. You see why you don't have to do this, but you can. And here's just a cheap quick delay function. I think macro that I made don't use those kinds of delays. They're bad, but anyways, we'll go over that some other time. Here's the prototype for the function. It's a static function, which means that it's only visible to this file. It's not visible outside of this file. You can take that away if you want. It's void because it doesn't return anything. I'm calling it print message. It's going to have a pointer to a character. Ooh, excuse me. I had like 4 slices of pizza. So yeah, it's a pointer to a character, which is going to be your message, and comma dot dot dot. What this means is that there are optional arguments that you can pass, but you don't necessarily have to, and there's an undefined amount. Okay, so the function doesn't know how many more arguments it's going to get. So that's how we do that in C. So that's our function prototype. All right, so let's get into our main here. One thing I wanted to show you guys. What the hell am I doing here? Or equals APB 2 enable register or equals 1 shifted 14 times. Okay, so what does this line mean right here? Okay, we know we're enabling something in the RCC register, in the APB2 enable register, which is we're taking a 1 and we're shifting it over 14 times. So let's go to RCC registers, APB2 enable register. A 1 shifted 14 times would end up right here. So that's UART 1 enable. That's the UART we're going to use, and I'm enabling it by putting a 1 here in the 14th bit. As you can see, a 1 enables the clock for the UART. Now, this is not exactly easy on the eyes, because 3, 4, 6 months from now, when I'm seeing this and other things like it, I don't know what exactly it's doing unless I comment here that, hey, I'm enabling the UART 1. Okay. So how do we make it more readable like this? Well, in your header file, which is this file right here, you have a lot of things. Every bit of every register is defined. So in other words, all these bits for all these registers, they are defined. So if you go up here and let's look for our RCC, here's RCC, right? And let's look at the APB2 register. Oh, must be higher up. APB2 enable register. Bit definition for the RCC APB2 enable register. So as you can see here, look at this. It says, let me make this bigger. It says RCC APB2 enable register UART 1 enable, and it defines this word as hexadecimal 4000. Well, what the hell is that? Okay, well, let's go here. Here's your standard Windows calculator. So if you just go to your Windows search bar and you put in calculator, you'll get this. Go here, you go to programmer, and you can type numbers. You can type the number 65, and that's number 65, and that's 65 in hexadecimal, that's 65 in octal, and that's 65 in binary. Okay, so we have the hexadecimal, what was it, 4000. So 4000 in hexadecimal is equal to this binary number. Now if I were to count these zeros, this is just a 1 shifted over 14 times. So this is defined to a 1 shifted over 14 times. Well, that's exactly what I'm doing here. So instead of typing 1 shifted over 14 times, I can just type that. I can just take this, copy it, paste it into there, and it has the same effect, right? Because a 1 shifted 14 times is hexadecimal 4000, and that's what that equals. So it has the same effect, except that it's much more readable. I can read this and say, okay, I'm enabling the UART 1. Okay, so that's what I did. So that's a little thing that I wanted to get to you guys. Use your header file. The vendor wrote it for you, and it's has everything defined. It's gonna save you a lot of typing and figuring things out. Okay. So now that you know where I got these all these little definitions here from, it's from the header file. Okay, so now let's go through it and see what's going on. First things first, here's our microcontroller, the F103C8 series. I'm going to be using UART1, and it's on port A10, which is going to be the RX, and port A9 is the TX. Since we're not doing any RXing, any receiving, excuse me, I've only set up port 9. So I've only set up port 9, which is the transmitter, because we're going to transmit to the serial port. So I've enabled that. I have to enable the clock for that port, for port A, and I have to enable the clock for UART1. Okay, and so here's UART1, and here's GPIO A register enable. I also have to enable the alternate function, because that's this right here. Because since I'm not using the pin as a GPIO, I'm using it as an alternate function, then I have to enable this alternate function peripheral here. Now, how do I know? Let's say I didn't have this software here, the CubeMX. If I didn't know that RX and TX on PA9 and 10, how do I know where they are? Well, you can go to your data sheet. You go back to your GPIO here, GPIO and alternate functions, and you go here to the alternate function configuration, and you can scroll down, and here it tells you all the pin mappings for everything. So for example, the analog to digital converter, the timers, timer 3, etc., a bunch of timers, UART3, UART2, and here's UART1. So UART1 TX is on PA9, UART1 RX is on PA10. Now, if for some reason you don't want to use those pins, or they're already being used for something else and you have to use UART1, you can remap them to be on PB6 and PB7. Well, how do you remap them, you may ask? Well, good, I'm glad you asked. So you're going to go to here to your alternate function register. And this one's called mapper, I guess. The map register. And as you can see, let's look for UART1. So here's UART1. It's on bit 2. Remap. Bit 2. Okay, so let's go to bit 2. Bit 2. Here's bit 2. UART1 remapping. So if this is 0, if you put a 0 in that bit, there's no remapping. That means TX is on PA9, RX PA10. If you put a 1 there, however, it will remap TX to PB6 and RX to PB7, and that's how you remap it. Easy, right? Easy peasy. But you remember, you have to enable this peripheral, the alternate function. You have to enable that in the here in the ABB2 enable register, which is right here. So that's why I enabled that. Even though I'm not remapping, I'm still using a pin as an alternate function, so I have to enable that peripheral. Okay, so now let's set up the GPIO port, because our ports, even though we're using them for something else that's not GPIO, we have to also tell them, hey, you're going to be used as an alternate function. So we're going to go to the control high register. Okay, back to the data sheet. So where are my GPIO? Here we go. Registers, control high register, because we're using pin 9. And remember, 8 through 15 is high, and 0 through 7 is low. So control register high. So we're using pin 9. So here's mode 9 and config 9. So mode 9 is just the speed. How fast do you want it to go up? Right? What's the slew rate you want? 50 megahertz, 2 megahertz. I set mine, I believe, at 50 megahertz. It doesn't really matter as long as you pick one of these and not that, not input mode, right? So here's mode, and I put, as you can see here, GPIO control high, mode 9 0 and mode 9 1. So this is defined. If you were to go here, definition of it, it says bit 0. So this hexadecimal, which if you put it into the calculator, this hexadecimal is nothing more than a 1 on bit 0 of mode for pin 9. And then this one is nothing more than a 1 on bit 1 of the mode. So these are defined as a 1 with a bunch of zeros and a 1 with a bunch of zeros, right? So I put both of them. I ordered this one and that one, so I will get a 1 1 right there. Now the important part, like I said, that doesn't really matter which of these three you pick. What does matter is the configuration. The configuration, since it's an output mode, it has to be alternate function output push pull. Okay, you don't want open drain, you don't want to be a general purpose IO, you don't want it like that. You want alternate function output push pull. That means you're going to make a 1 here, 1 0, so it's going to be 1 0. Now you have to also notice what's the reset value of this configuration bit. The reset value is this 0 1. So 0 1. So there's already a 1 here, but you want 1 0, so you have to make that 0. I made the mistake earlier that I put a, since I wanted 1 0, I put a 1 here and I didn't do anything to this bit because I'm like, they all default to 0. But that's not the case. Here the default is 1, so there's already a 1 here. So by me putting a 1 here, I actually made it 1 1, which means this reserved. It's an undefined state. It's not going to do anything. And I was trying to figure out what happened, and I forgot that not everything always defaults to 0 0. Okay, so you have to write a 1 here, and you have to clear this bit. You have to write a 0 here, and that's what I did in my my code here. I wrote the 1 1 for the mode, and I wrote a 1 for the bit 1, and I wrote a 0, or I cleared the bit 0 of the config. So here's config 9 bit 1. There's a 1 in there, and here I did the AND complements operation to clear the 0th bit. So now I have a 1 0 in that configuration. Okay, so that's the setting up of the GPIOs and the clocks. Now let's go to the how do you find the baud rate. So now we're going to be setting up our UART, which is so easy. It's only 3 lines. It's got to be the easiest thing to set up. So how do we find the baud rate? You know, you know what baud rate you want, but how do you type it in? Well, what has to happen is, if we go to our data sheet here, we go to our UART, which is right here, interrupts, registers. Okay. So we have our status register, which we read from. We don't really write to it. Here's our data register, which is where we're going to type our data or send our data, whatever. Here's the baud rate register. Baud rate register is divided into 2 sections. The mantissa, I don't know if I'm saying that right, and the fraction. Okay, so what does this mean? All right, so here's a little formula. You're going to take your clock of your peripheral. In other words, my microcontroller is running at 72 megahertz, okay, and so is the APB2 bus, 72 megahertz. You're gonna divide that, or yours could be running slower, whatever you're running your chip at. So you're gonna divide that by the baud rate that you want times 16, and you're gonna get a number. In my case, I got 72 million divided by 9600 times 16. I got 468.75. So you're going to take that 468, you can convert it to hexadecimal, okay? So we get our programmer calculator. So in decimal, we have 468. That's 1d4 in hex, okay? 1d4. So right there, I have 1d4. Now you're going to take the fractional part, which is 0.75, and you're going to multiply it by 16. So let's go 0.75 times 16 gives you the number 12. 12 in hex is easy. So 12 in hexadecimal is C. So 1D4C will be the number that you're gonna have to put in your UART1 baud rate register to get that baud rate that you want, or that I want, of 9600 kilobytes per second. Now the other thing we have to enable is the transmitter in control register 1. So we're gonna go here, control register 1, bit 3 TE is down here. Bit 3 is transmitter enable, so we're going to enable our TX pin, and then we're also going to enable our UART enable, which is bit 13. And that's what I did here, and the same thing with this. They're already defined in the header file. Okay. How do you know what's defined in the headers file? Well, look for the peripheral you're using, and it'll have bit definitions for everything. Okay, so here's our while. We'll get to that in a minute. Now here's the meat of this thing. So I explained this already. It's just a pointer to the character array that we're going to send it, but we have an undefined amount of arguments we can pass. And they're also optional. You don't have to pass any arguments. So we're gonna make a buffer, right? This is gonna hold our message temporarily. This just means that if I've defined a debug UART, then it will go ahead and compile this, and if not, then it won't. That's all this means. This if def and if. You don't even have to do that. You can just make it as a normal function would be. So we're making a list of arguments, right? VA list. Now this comes from this argument library. I'm not exactly sure what it does, but here's the gist of what this actually does. So we're passing it our message, okay? We're passing it our message, and what it's going to do, it's going to extract all the arguments. What are the arguments? It's this stuff right here, %D, %C, %F, whatever printf arguments you want to pass it. It's going to extract them all, and it's going to take your message and reformat it to how you want it to be given the arguments that you used. And it's going to take that newly reformatted message, and it's going to put it into that buffer. Okay, so then what we're going to do is we're going to go through that buffer, which was an array, remember, and we're going to start printing that basically character array, character by character. And we're going to do a little for loop from 0 all the way to string length, right, of that buffer, because we're not sure. We've defined it to be 80, but our message may not be 80. Maybe our message is only 10 characters long. So we're going to get the length of that buffer, and using the string length function. That's why we need I'm not sure if string length, yeah, it's probably in strings. So yeah, so from 0 to string length plus, and then to simply print to our UART, we just into the data register, which is an 8-bit register. Don't forget that. I know this is a 32-bit microcontroller, but ASCII characters and all that good stuff, it's only 8 bits. See, data register right here, 8 bits. The rest is reserved. So we're gonna put into that register whatever character we have at our current index of I, and we can't just do this at full speed because we're running at 72 megahertz. The UART is only running at 96 kilobits per second, right? So we have to wait until that transmit buffer is empty, until it's finished transmitting, basically. So we're gonna check our status register. We're gonna take the entire value of our status register, and we're gonna end it with the value of a 1 at a certain bit, right? Because that's what this TXC it translates to a 1, where a 1 on the what is that, 8th bit. Okay, and if we go here, status register, or not 8th, 7th. So a 1 right here, TXE, means that the transmit data register empty. That means the transmit data register is empty. That means it has transmitted. That means it's set by hardware when the content of the TDR register has been transferred into the shift register. So the way the UART works is you type data into the data register, and then it shifts it via a shift register onto whatever method it uses to actually transmit, and then your data register becomes empty. So then you can now type in new data. So we're going to be checking this. So if there's a 1, that means it's been transferred to the shift register. That means you're good to go. That means we're ready, right? If there's a 1 in there. But we're checking here if there's a 1, but we don't want to hang in this while loop if there's a 1, because that means it's empty. We want to hang here if there's a 0, because that means it's not empty. So right here we're checking for a 1, but then here we're nodding it, so in reality we're checking for a 0. So we're going to hang here in this while loop as long as there's a 0 in that TXE bit, and then we'll go on to the next one. And that's how that works. And then you can call your function, hello, I am %D years old. D will be right here, but this you can do anything, really, anything that will return a number or a counter or whatever it is you want. And then you can send it to your microcontroller. You go here, you go to your COM port. How do you find your COM port? I'm not sure if I already showed that in the beginning, because like I said, I've made this video twice, but here it is. It's showing me my USB to serial is on COM 12. Okay, and I know that I set up my hardware to be 96 kilobytes per second, and the parity bit, data bit, all that stuff is default, just how I left it also in the microcontroller. You press OK, you go here, right? You set that up, you press OK, and then it just starts printing. You can use this to clear once your screen gets full. You can type in hex, I guess, or just view it as text. And the beauty of this is that let's say if I don't want this to print 65 as a number, let's say I wanted to print it as a character, I put C for character, and I know that 65 is A, so we'll do that. We'll upload it again, and see, now it's printing A's instead of 65. Oh Jesus. Okay, so I'm done. That's it. I hope I explained it well. If you have any questions, let me know. It's a long video and it's a lot of talking, but this is all the code there is. It's 3 lines to set up your UART, 3 lines for your clocks and your pins, and like maybe 6 or 7 lines of actual code, okay, for the print function. And it's good. It helps with debugging, and it's great to use. And it's you can even take all of this and put it in a header file, and make a little C file for it, and just save it into your where these libraries are saved. You can save it in the same folder, and just include my debug UART in all your projects. And all you have to do is type this debug UART, define it, and it'll compile that function for you, which is why I have it set up this way. And that's it. So in this case, see how I have debug UART equals UART1. If this were actually in a different file, I would just, instead of UART1, I'll take this right here and I would do that, and it's the same thing because debug UART is defined as UART1. Okay, so there you have it, guys. Bye bye.